In this video, possibly to begin with, we're going to learn how to compute and interpret the mean and standard deviation of a discrete random variable when given its probability distribution. In other words, for you to be able to compute the mean of a discrete random variable, you must be provided with the possible values of x and the respective probabilities of each of the possible values of x, otherwise called the table of x values and its probabilities, or the discrete probability distribution table. So, before we get started, we must ask ourselves, what is the relevance of computing the mean and the standard deviation of a discrete random variable? It is because the mean and the standard deviation can be very useful in describing the center or the typical values of the random variable, how values are spread around this central value, and the shape of this distribution. In particular, we're going to use the mean to describe the center and the standard deviation to describe the spread. In the long run, this can be extended to finding values that are unusual in the set of all possible values of a random variable. So without any further ado, let's consider the first example. A small statistics class of 10 students was asked to disclose the number of people living in their households. The following data was obtained: 2, 4, 6, 6, up until 5. What is the mean number of people living in their households? Well, what would we do? There is a traditional way we could find the mean. We'll add up all the data values and divide by 10. That is one way. In fact, we're going to start out that way and then show that there is a different approach. And in that way, we'll be able to generate the formula in general for calculating the mean of a discrete random variable. Let's see. So if I wanted the mean, as we just discussed, I would add up 2 plus 4 plus 6 plus 6 plus 4, all of the numbers all added together. Now, just as a mini exercise, I'm going to regroup all the 2's together. So I have 2 plus 2. Then all the 3's together. So I have just 1, 3. And then all the 4's together. 1, 2, 3. So here we go. And all the 5's together. And all the 6's together. All divided by 10. So it appears I'm going to have what? How many 2's here? So this is 2, that will cause twice. And then I have 3, that will cause once. I have a double plus there. I don't need that. And then you have 4, that will cause 3 times. And then I have 5, that will cause twice. And I have 6, that will cause twice, all over 10. This can break up into this piece over 10. So I have 2 over 10 plus, the next one is 3, 1 over 10 plus 4, this is 3 over 10, and then plus 5, that will be 2 over 10, and then plus 6, 2 over 10. This line is equivalent to this line. So, as it stands, what you observe is that this is the sum of each possible value of x, each possible value of x multiplied by their respective probabilities. And we can see that in this table. So this is 2 multiplied by 2 over 10 right here. And then 3 multiplied by 1 over 10 right there. And then 4 multiplied by 3 over 10. 5 multiplied by 2 over 10. And 6 multiplied by 2 over 10. So, as it stands, we have a generalized formula, and that is summarized in this table. for the mean of a discrete random variable, we will take each possible value of x, we'll multiply it by its respective probabilities. So we'll get different values, a number of different values, and then at the end, we'll sum it all together in order to arrive at the mean of a discrete random variable. At this point, we want to ask ourselves, what does this mean of a discrete random variable do for us besides being a measure of central tendency? The answer lies in another name for the mean of a random variable, and that is the expected value. The mean, denoted by mu. In order to write mu, I usually suggest writing capital U and then extending the bar. This is pronounced mu. If you like cats, then that might be easier to pronounce. So, the mean is exactly the same as the expected value, and that is provided here. The expected value of a discrete random variable is exactly the same as the mean. Calling the mean the expected value helps us to introduce some dimension to the meaning of the mean in the context of a discrete random variable, because the mean or the average value represents what over the long term of doing an experiment over and over again, this is the number you would expect on average to represent the random variable as a typical value. Let's take an example. Suppose Nancy attends classes 3 days a week. Yes, we saw this example earlier. She attends classes 3 days a week, 80% of the time, 2 days, 15% of the time, 1 day, 4% of the time, and no days, 1% of the time. We're going to let x be the number of days Nancy attends classes weekly. What values does x take on? Well, she could attend classes no days, 0, 1 day, 1, 2 days, 2, or even all 3 days of the week when she was planned out, or when she has planned out to attend classes because she has classes on those days. So now suppose 1 week is chosen randomly. We're going to construct this probability distribution table, which we did earlier, and then we're going to find the expected value of how often Nancy attends classes a week. So first of all, let's create the probability distribution table, 0, 1, 2, 3, and then she attends classes no days 1% of the time, so that will be 0.01. Then 1 day, 4% of the time, 0.04. And then 2 days, 15% of the time, 0.15. And 3 days, 80% of the time, 0.80. In order to get the expected value, which is otherwise written as E of x, this is the first step we take. We look back at the formula we generated. We're going to multiply each possible value by its respective probability. Let's create a column for that. Each value, x, multiplied by the respective probability. That is the first step. So 0 times 0.01 is 0. 1 multiplied by 0.04, 0.04. 2 times 0.15, 0.30. And then 3 multiplied by 0.80 is 2.40. Then, after we have generated the separate products, what do we do according to the formula? We're going to take the sum of these products. So it means we're going to add up this 0 plus 0.04 plus 0.30 plus 2.40, and that will be equal to the expected value that this question wants. Remember, the expected value is exactly the same as the mean, which is otherwise written as mu. So this will be equal to what value? That will be equal to 2.74. So it follows that we expect that if Nancy continues to attend classes frequently, continuously over and over and over again, on average, she will attend classes about 2.74 times a week. This is not bad. Then, with that said, we proceed to the concept of the standard deviation of a discrete random variable. How do we get that? Actually, the formula is provided here. And as overwhelming as it looks, we can actually walk through it. Let's unpack what this formula talks about. A more relatable version is this one I am circling, that is the one below. This one is more relatable. You see, the first one here, that is the first piece in this formula, is mu of x squared. To keep it simple, remember we got mu of x here. Mu of x is right here. So the square of this mean, that is 2.74 squared, will be what's going here. Then the other part requires us, if you observe closely, to square each value of x and then multiply by the probabilities and then add them up together. To do that, let's begin. First step, create another column of x squared. That is, each value of x, 0, 1, 2, 3 squared. So 0 squared is 0. That 0 came from here. And then the next one is 1 square, then 2 square, and then 3 square. We're going to populate that here. So let's do that. So you have 1 square is 1. You have 2 squared is 4. 3 squared is 3 times 3, which is 9. Then, looking back at the formula, each x squared should be multiplied by its respective probability. Sure, we can do that. X squared times p of x. That is, as it stands, let's put away some of these lines. Okay. All right. So we have x squared, that is each x squared, multiplied by p of x. So that will be 0 times 0 0.01, that is 0. And then 1 multiplied by 0 0.04, that is still 0 0.04. However, 4 times 0 0.15 is 0 0.60. Then 9 multiplied by 0 0.80, that is 7.20. So, as it stands at this point in time, what we want to do next is this summation means to sum all of the answers we got for x squared times p of x. That is, we should sum up all the numbers in the last column. So, in this way, we're saying that the standard deviation here will be the square root of the sum of these numbers. That is what this represents. That is coming here, minus the mean square. Well, the mean we got was 2.74, so 2.74 square is coming here. So let us get this question mark. That is, let us add up 0 plus 0 0.04 plus 0 0.60 plus 7.20. That will be equal to 7.84. And if you take 7.84, subtract 2.74 square, and then take the square root of the answer, what do you get? 0.5765414. This is the standard deviation. Standard deviation of x is written as, put the 0, then put a bar over it. Then, if you like, you can put x, and if you like, you can keep it as a generic one. We can write either standard deviation, sigma subscript x, and this is pronounced sigma. It's pronounced sigma, and it represents the standard deviation of a discrete random variable. Well, not all the time would we be required to go through all these calculations. So let's see if there's an alternative way we can deploy technology in order to help us make these computations easier to access. In order to use technology here, what I will do is this. I will key in, to begin with, my probability distribution table. That is, the possible values of x in the first column and the probabilities in the second column. I'll key them into StatCrunch. So here I have them in StatCrunch, 0, 1, 2, 3, and then the respective probabilities. Then go straight to Stats, go to Calculators, go down to Custom, click on Custom. You have stored the values, the raw values in the variable x and the weights in probability of x, and then click on Compute. And there you are. You have the graph, then you have the mean, and you have the standard deviation. If you need to compute probabilities too, you can also compute that. For now, we concentrate on the mean and the standard deviation, and you can observe that all the values we have here matches exactly what we did by hand earlier, where we got the mean to be 2.74 and the standard deviation to be 0.5765,414. In this case, we can see that solutions by hand will match exactly the same solutions that technology will provide. So from here on out, we're going to be using technology since it helps us to get the same answers. And then we will focus on the interpretation and the use in business or real life context.